Hi, I'm Dr. Matt Turner, and you're watching a video lecture for ECET 273 Modern Energy Systems at Purdue University in New Albany. This video is part 2 of a two-part module on energy, force, and power. In the first part of Module 1, the concepts of energy measured in British thermal units and power measured in watts were introduced. Obviously, these terms are related but mean different things. For example, we often refer to the location that electricity is produced at as a power plant, while the output of machines such as solar panels and wind turbines are often referred to as renewable energy sources. In this module, these and other basic energy concepts are more fully explained and their interrelated nature is analyzed. Let's start by investigating the concept of energy. The etymological origin of the word energy is two Greek terms, the first en, meaning to cause a person or thing, and the second ergon, meaning work. The work energy, therefore, is the combination of these two terms, meaning to cause work. In physics, energy is strictly defined as the capacity for doing work. Both of these definitions reveal that it's pretty difficult for us to quantify energy as a thing. As the famous American physicist Richard Feynman stated, we really don't have a picture that energy comes in little blobs of a definite amount. Instead, our scientific understanding of energy is based on the amount of work that a physical system can do on another physical system. What we really say is that energy is an indirectly observed quantity, which means to say that we see the work that energy does, we don't actually see the energy itself. For example, burning wood through combustion is a sequence of chemical reactions that produces heat and chemical byproducts. The release of the heat produces lighter flames. In this process, energy from sunlight has been stored as chemical energy by a plant in the wood via photosynthesis. The energy is then released as thermal energy when the wood is combusted. Processes such as burning fuels, propelling machines, and charging batteries are all examples of energy transformation from one form to another. These forms include the kinetic energy of moving objects, the electric energy transferred by electricity, the gravitational energy due to the position of an object or the arrangement of particles in a system, and the nuclear energy released when the nucleus of an atom is split into neutrons and protons. Energy is a scalar physical quantity measured in the SI units of joules, and by scalar we mean that it only has a magnitude. Energy is a derived unit and can be defined in terms of the SI base unit as mass units multiplied by velocity units squared. So 1 joule is equal to 1 kilogram, which is the mass SI unit for mass, times the unit for velocity. Velocity is a derived unit, it's meters per second. We square that to get energy, so we end up finding that a joule is a kilogram meter squared per second squared. Due to the many forms of energy, other units than the joule will be commonly encountered in this course, as shown in this table of energy unit conversion factors. For example, 1 foot-pound force is equal to 1.3558 joules. A foot-pound force is the unit of energy in the English Standard System. British thermal unit is the amount of energy needed to cool or heat 1 pound of water 1 degree Fahrenheit. The unit of horsepower hours is typically used with motor loads. Kilowatt hours are used by the electric power industry, the electric companies. A calorie is the thermal energy needed to heat 1 gram of water by 1 degree Celsius if the pressure is at 1 atmosphere. A barrel of oil equivalent, or a BOE, is very important. It's the energy released by burning 42 gallons of crude oil. And a therm is the energy released by burning 100 cubic feet of natural gas. So a lot of these energy units refer to the energy that are stored in fuels. So let's do an example converting between energy units. And we'll tie it into maybe your energy bill that you might receive from your local electric or gas utility. So we've got a residential customer, and in the month of January, aggregated, he used 2.048 times 10 to the 7th BTUs of heating energy. So that's how much it took to heat his house total for the month of January. He has a choice now. The utility bills natural gas at a rate of $1.12 per therm of natural gas, and they bill electricity at 6.3 cents per kilowatt hour. he has his choice between two machines, a 70% efficient gas furnace or a 100% efficient electric heater. Which option should this utility customer choose? So let's do the analysis of this here. So the first thing that we need to do is we need to calculate the therm and kilowatt hour equivalents of the 2.048 times 10 to the 7th BTU. So we need to convert the BTU energy into its other two types, therm and kilowatt hours. They're all energy units. They all measure the same thing. They're just different units. So 2.048 times 10 to the 7th BTU into therms first. So for natural gas, it's 2.048 times 10 to the 7th therm, THM. So that's 2.048 times, or sorry, 10 BTU. That was our original quantity. And we need to convert that over to therm. Well, to do that, we're going to convert first to joules. So we do 1055 joules per BTU, 1055 joules per BTU. And then we need to convert from joules to therms, and one therm is equivalent to 105.5 times 10 to the 6 joules. So one therm is 105.5 e to the 6 joules. So what that tells us is that the conversion for natural gas, 2.048 times 10 to the 7th BTU, if we were going to have that in therms, it's equals 204.8 therm. So now we can figure out how much natural gas is. But first, let's do the kilowatt hour equivalent. So we got some lightning there representing our electric energy. So what we're going to do is calculate the kilowatt hour equivalent of the 2.048 times 10 to the 7th BTU. So we start the same way. We do 2.048 e to the 7th. It's the same as 10 to the 7th BTU. We multiply that by 1055 joules per BTU. So 1055 joules per BTU, and then we need to know the kilowatt hour equivalent to a joule, which is 3.6 times 10 to the 6. So 1 kilowatt hour is 3.6 e to the 6 joules. And what does that give us? 6,001.8 kilowatt hours. So what have we shown here? We've shown that 2.048 times 10 to the 7th BTU is the same as saying 204.8 therm, and it is the same as saying 6,001.8 kilowatt hours. They're all measuring the same amount of energy, just different units, right? So now what we need to do is use our efficiency and the cost of the fuel input sources to calculate total cost for this energy. So we'll clear our slide. So to calculate the total cost, we just take the value of energy measured in therms. So again, for the natural gas, it's going to be 204.8 therm. Here we have to do a conversion. The furnace that we've selected is only 70% efficient, which means we've got to put more heat energy. We need to put more energy in the form of natural gas fuel than we get out in heat. So to figure that out, we take 204.8 therm, we divide by the efficiency of 0.7. Right? So then we just multiply that by the cost that the utility is billing, $1.12. This is a pretty realistic figure for the cost of natural gas, by the way. So we multiply that by $1.12 per therm, and we come up with $327.68. So I would not be particularly happy with that bill, but let's see what the difference is if we calculate it for electricity instead. So for electrical energy, we determined that we needed 6,001.8 kilowatt hours. It's a resistive heater, and one of the interesting properties of a resistance is that they convert all electrical energy in them into heat, so they're 100% efficient, as we stated on the previous slide. Now we multiply that by 6.3 cents per kilowatt hour. Turns out that that's $378.11. So if we do the calculations, and despite the fact that the gas furnace is only 70% efficient, it turns out that it's about $50 cheaper to operate that due to the lower cost of natural gas.